Section: Introduction. In this section, we discuss the growing use of large language models, LLMs, in various applications, from chatbots to coding tools. However, this rise has also led to security issues, particularly with prompt injection attacks, where attackers manipulate the model's responses through specially crafted inputs. One notable type of these attacks is jailbreak prompts, which can bypass safety measures and lead to harmful outputs. Recent studies have identified prompt injection as a significant risk, highlighting the urgent need for effective defenses. We focus on a specific type of attack that uses adversarial suffixes, malicious sequences added to prompts, to disrupt LLM behavior. Research has shown that even advanced models like GPT 3.5 and ChatGPT can be tricked into producing inappropriate content by adding these suffixes to otherwise harmless prompts. In our threat model, we consider an attacker who can only modify the user's input by appending a harmful suffix, without access to the model's internal settings. The original user prompt is assumed to be safe, while the suffix is intended to mislead the model. This scenario reflects real-world situations where malicious users might insert hidden instructions into their queries. We also review existing defenses against such attacks. Some methods involve adversarial training, where models are trained on malicious examples to improve their resistance. However, this approach can be resource-intensive and may not be practical for large models. Other strategies include using safety filters that monitor inputs and outputs without changing the model itself. While these filters can be effective, they often have limitations, such as being easily bypassed by clever attackers or producing false positives. Recent research has explored using perplexity, a measure of how unexpected a prompt is for a model, to identify adversarial inputs. However, this method primarily detects rather than mitigates attacks. We introduce an erase and check framework that aims to provide certified safety by systematically removing parts of the input and checking for harmful content. While promising, this approach can be computationally demanding. To address these challenges, we propose Adversarial Suffix Filtering, ASF, a lightweight and model-agnostic defense mechanism. ASF acts as a sanitizer for incoming prompts, identifying and removing adversarial suffixes before they reach the LLM. Our method maintains the original model's performance and can be implemented in secure environments, protecting models from adversarial manipulation even when interfaced with untrusted applications. Our approach is inspired by previous work that demonstrated the potential for LLMs to generate adversarial suffixes, suggesting that these suffixes follow identifiable patterns that can be classified by another model. Section Summary. In this section, we discuss the rising security concerns associated with large language models, LLMs, particularly focusing on prompt injection attacks, such as jailbreak prompts and adversarial suffixes, which can manipulate model behavior and bypass safety measures. We propose Adversarial Suffix Filtering, ASF, as a lightweight, model-agnostic defense mechanism that sanitizes incoming prompts to detect and neutralize these malicious suffixes without altering the underlying LLM. Section: Methodology. In this section, we describe our Adversarial Suffix Filtering, ASF, pipeline, which aims to identify and eliminate harmful suffixes added to user queries. We define our threat model where an attacker can combine a regular user query with a malicious suffix. This suffix, often nonsensical or specifically designed, aims to bypass the safeguards of a language model, leading it to generate inappropriate content. Our focus is on detecting and removing these suffixes. Our pipeline processes an input text that may contain a malicious suffix through several steps. 1. Segmentation. We break the input into segments that resemble sentences using a cutting-edge segmentation model. 2. Segment classification. Each segment is analyzed by a binary classifier to determine if it is part of an adversarial suffix. 3. Post-processing. We refine the classifier's predictions to group contiguous malicious segments and apply checks to minimize false positives. 4. Filtering. Segments identified as malicious are removed, resulting in a cleaned query that is sent to the language model for safe processing. We utilize the segment any text SAT model for segmentation, which effectively identifies sentence boundaries without relying solely on punctuation. We chose the largest SAT model variant for its superior performance. For classification, we fine-tune a BERT-based text classifier to detect adversarial suffixes. This model is lightweight and provides a strong understanding of context, allowing it to recognize subtle indicators of malicious content. We treat the detection task as a binary classification, where each segment is labeled as either benign or malicious. To train our ASF system, we compile a dataset of benign prompts and adversarial suffixes, the latter sourced from existing datasets. We ensure a diverse range of benign queries and create prompt suffix pairs for training. During training, we derive segment-level labels from these pairs and fine-tune the BERT classifier, monitoring its performance on a validation set to avoid overfitting. After classification, we apply two post-processing steps: smoothing labels to correct misclassifications and filtering segments based on specific keywords to reduce false positives. Finally, we either remove flagged segments or raise an exception, depending on our configuration, and reconstruct the sanitized prompt from the remaining segments. Section Summary. In this section, we describe our Adversarial Suffix Filtering (ASF) pipeline, which detects and removes malicious suffixes from user queries to prevent harmful outputs from language models. Our methodology includes segmenting the input text, classifying segments as benign or adversarial using a fine-tuned BERT model, and applying post-processing heuristics to refine predictions before sanitizing the query. Section: Experiments. In this section, we conduct an empirical evaluation of our proposed ASF pipeline, focusing on two main areas: I. Its effectiveness in detecting and neutralizing adversarial suffixes from advanced attack methods, and E. Its robustness in non-adversarial situations, particularly regarding the preservation of model utility. We perform all experiments using the default ASF configuration, which includes smoothing and keyword-based post-processing. For evaluating adversarial robustness, we measure the attack success rate, ASR. We consider an attack successful if at least one of the generated suffixes successfully tricks the model into providing an adversarial response. This approach reflects a realistic scenario where multiple attempts may be made, and even one successful bypass indicates a failure in defense. Our experiments were carried out on a dedicated compute cluster with multiple GPUs over about 3 weeks, and we plan to share our code and trained models on GitHub to encourage reproducibility. In adversarial settings, we first assess the performance of our BERT-based segment classifier on validation and test datasets derived from our prompt suffix dataset. We achieve an F1 score of 98.5% on the validation set and 98.4% on the test set, confirming that ASF can effectively differentiate between benign and adversarial segments. However, high accuracy on synthetic data does not fully reflect ASF's real-world impact on ASR mitigation. We evaluate adversarial performance using two benchmark datasets, malicious instruct and advabench, generating adversarial suffixes with 4 generative attack models. We use harmbench to determine if a model's response to a prompt suffix pair is a jailbreak. We exclude vicuña models from testing since they already produce jailbroken responses in over half of the cases without any adversarial suffixes. We also note that GPT 3.50125 is easily tricked, with a benign ASR of 2.7%. For example, an original prompt about teaching children to use firearms was successfully tricked by adding a natural-sounding suffix. After our sanitization process, 76.4% of the suffixes were completely removed, leaving the original prompt intact. In 2.9% of cases, the sanitized prompt was empty due to misclassification or overlap issues. Our defense effectively reduces ASR, demonstrating that ASF can neutralize attack effectiveness in practical settings. In non-adversarial settings, we evaluate whether ASF negatively impacts LLM performance during benign usage. We conduct tests across standard natural language understanding and generation benchmarks using 3 models: Llama-3.1-8b, Mistral 7b Instruct v0.1, and GPT 4.1 Mini. For GPT 4.1 Mini, we focus on generation-based evaluations due to API limitations. We also assess log likelihood-based tasks for the open-source models to get a comprehensive view of any potential performance degradation. Our results show minimal impact across all tasks and models, with most variations falling within normal ranges of generation variability. Overall, these findings indicate that ASF does not significantly degrade model performance in non-adversarial contexts, suggesting it can be safely integrated into production systems without compromising output quality for legitimate users. Section Summary. In this section, we empirically evaluate the ASF pipeline's effectiveness in detecting and neutralizing adversarial suffixes while ensuring model utility in non-adversarial settings. Our results show that ASF significantly reduces the attack success rate (ASR) against various attack models without negatively impacting performance on standard natural language tasks, indicating its safe integration into production environments. Section Discussion. In this section, we discuss the importance of robust defense mechanisms like adversarial suffix filtering (ASF), as large language models (LLMs) become more integrated into real-world applications. One major benefit of ASF is its model-agnostic design, allowing it to be placed in front of any commercial model, such as GPT-4 or Claude APIs, to intercept harmful suffixes without needing to access or change the model's internal structure. This makes ASF easy to deploy as a plug-and-play component, requiring minimal engineering effort to integrate into existing AI systems. ASF is efficient, using about 387 million parameters across two small models, which only adds around 1.7 gigabytes of GPU memory. Unlike heavier defenses that need multiple passes through the main model, ASF inspects inputs in a single pass, resulting in very little delay. Importantly, it does not increase the token usage or inference time of the target model, ensuring that the performance on regular tasks remains unaffected. However, we must acknowledge some limitations of ASF. It relies on accurately separating user prompts from appended suffixes, which can sometimes be challenging. While most prompts and suffixes do separate cleanly, there are instances where the system might misidentify benign and malicious text, potentially removing more than necessary. Additionally, there is a risk of false positives, where harmless content is incorrectly flagged as adversarial. Although we found that simple post-processing rules can help reduce this issue, the need for these rules suggests that careful calibration may be necessary for different contexts. Currently, ASF is designed to be cautious, prioritizing security over specificity, which could lead to inconveniences for users if legitimate queries are mistakenly rejected. Developers using ASF should monitor its performance and adjust filtering policies to find a balance between safety and user accessibility. Furthermore, ASF is specifically tailored for suffix-style attacks, which may limit its effectiveness against other types of prompt injection techniques. If a new attack method does not involve a clear suffix, ASF might not detect it without further modifications. We envision ASF as a key component in broader LLM security frameworks, acting as a lightweight, real-time filter to identify and neutralize adversarial suffix attacks. Its low computational demands make it ideal for environments where speed and resources are limited. Additionally, ASF can serve as a trigger for more complex defense strategies, escalating inputs to more intensive defenses when necessary. This layered approach aligns with the Swiss cheese model in risk management, where multiple defense layers work together to maintain system resilience, even if some layers are bypassed.